Okay, so we're at the last lesson. We're skipping around a little bit. 9.5 we basically already talked about. It's a bit more with elastic collisions, but we've already done stuff with that. So we're skipping to this last lesson, impulse. So to introduce the concept of impulse, let's look at this scenario first. You're driving your car and accidentally run head on into a tree moving pretty fast. You accidentally forgot to put your seatbelt on. What's going to happen? What's the role of your airbag in your car? Just obviously, we know what's going to happen, right? You're not wearing a seatbelt, so there's nothing there to prevent you from moving. You do have the airbag, though, so think for a bit what is going on in this situation. And think about that airbag. So we're going to come back to that in just a little bit. So impulse, what this impulse is, it's the external force on an object multiplied by the time of the collision. The time of the contact in particular is what this is referring to. We're going to call this later time of contact. So this is the formula for impulse. Some external force acting on an object. So this is specifically, again, two objects colliding. But we're talking about one object. The external force is the other object. That's what it's saying. Times the change in time, so how long they were actually in contact, is going to equal a change in momentum. So impulse is actually defined as a change in momentum. Now this is referring to a change in momentum in one object. We've talked about how in a collision, momentum is conserved. That's talking about the total momentum before equals the total momentum afterwards. This is talking about looking at one object's change in momentum. Because again, the whole point is, yes, the total momentum of the system before and after, adding the momentums is the same. But the momentums of the individual objects can change. So again, don't get confused. This is specifically referring to the change in momentum of one object, not the change in momentum of two objects colliding, because again, that is conserved. That stays the same. That doesn't change. So a change in momentum of, again, an object, we're looking at one object, has to be due to an external force. This is basically going back to Newton's second law, an object in motion stays in motion. Newton's second law. Okay, this is basically going back to Newton's first law that an object in motion tends to stay at motion. So we need, for a change in momentum to occur, we need to have our object colliding with something. Otherwise, that momentum is not going to change. Colliding, or of course being impacted by something. So friction we can call an external force as well. We're mostly going to be looking at collisions here. So in order to change momentum, if we actually want to change the momentum of an object, if I have a train barreling down, in order to get that train to stop, based on this formula here, you need one of two things. You either need a huge force. You need the force to be big in order to change the momentum of that train, yeah? If it's just a fly standing in front of the train going, stop, it's not going to do anything, yeah? It's not going to be able to exert a great force. Or what we need is a long contact time. Even if the force is not that great, if the force is applied over a very long time, that will cause a change in the momentum. Yes, of course, the fly is never going to change the momentum of the train, but we talked about that as a special case, that the fly's mass versus the train mass is just so different that no matter how long the fly is squashed onto the windshield of the train, it's not going to change the momentum of the train. But still, like Superman, you could think Superman. The mass of Superman is not that great, but he is able to withstand the force of the train because he's so strong. So he can stand there and push the train, and even though he may not be able to apply that much of a force, he's able to withstand the impact of the train, so he can stay there in front of the train for a very long time and eventually cause the train to lose momentum. So again, if we want to have an object's momentum changed, we either need to impart a great force on that object or imply a smaller force, but for a very long time. We keep that force applied. So let's think back to the car crash scenario then. So before the collision, the steering wheel is at rest, but your face is moving very quickly, right? The collision meaning your face to the steering wheel, right? You've already collided with the tree, which means your car has come to a stop. But because you're not wearing a seatbelt, your face is still moving as fast as you were driving. This is why we have seatbelts, yes, to prevent us from flying out of the windshield. So before your face collides with the steering wheel has already come to rest because the car has already hit the tree. But again, you are still moving towards that steering wheel. So there is momentum in the system. It's your face, right? Moving towards the steering wheel. After the collision, meaning after your face collides with the steering wheel, both things are at rest. Your face is there just squished into the steering wheel and is at rest. So you lost momentum, right? Now, if there was no airbag, you would lose that momentum very quickly, right? The contact time would be very short. There's your face into the steering wheel. That means it would be a very large force stopping you. Because the contact time is so small, in order for you to lose all your momentum, that force is going to be a lot, which should make sense because that hurts, right? So in this case, what airbags do is they extend the contact time. When they pop out like this and then slowly deflate, they are increasing the time it takes for your head to come down. And again, they have a much less force applied than the steering wheel would on your face, but they are increasing the time it takes for you to come to a stop, right? Again, that airbag comes out, you hit the airbag, and then it slowly starts to deflate. So it is increasing the time it takes for you to lose all of your momentum. So just to kind of summarize this, we kind of said a couple things here, but I want you to write a sentence just to think about this. In situations like car crashes with airbags, or I'm sure you guys have seen stuntmen jumping into those huge inflated bags was the only thing I could think of, but you know, they're just basically huge inflated beds that they can jump into to jump off buildings. So why do you think it's safer for the person that the purpose of these safety measures is to extend the contact time versus exerting a larger force on the person? Again, the point of these things, these airbags, I guess you could call this an airbag as well, is to have the person come to a stop, right? So these things, again, extend the contact time it takes for them to come to a stop versus exerting just a massive force on them. Why do you think it's safer? Put it in a sentence. So something you could have said is because, of course, if it's a larger force, that is going to do a lot of work on your body. It's going to hurt, right? Obviously, if we didn't have that huge inflated bag for that stuntman to jump into, he would stop. He would still stop as intended, but he would stop very quickly. Come in contact with the ground and he has stopped. That contact time is like nothing. Therefore, in order for him to lose all of the momentum, the force is a lot, and that hurts, right? If we extend the contact time, once again, the force can be smaller. And I'm going to show this real quick here, actually, just as a quick example for you to follow along with. Say that your momentum, let's say your mass, is about 50 kilograms. This is a little example we're doing here. And your speed or your velocity, let's say you're falling, why not, off a building, is 10 meters per second. That's the speed that you are going right when you come into contact with something that is going to change your momentum, an external force, right? So to start with, what is the momentum we have here? There's the mass, there's the speed. What's the momentum? So momentum is once again mass times your velocity. So 50 times 10. So your momentum is 500. Don't forget these units, guys. Remember, it's not anything special for momentum. It's just kilograms times meters per second. So this is your momentum. So impulse, which is again force times change in time. I forgot to say this, guys. Impulse does not have a variable. This is impulse. It's not, we don't say I equals. Yeah, this is impulse by itself. If you see that, you would read that. You could read that as impulse. So impulse equals our change in momentum. So say that you jump off a building and you are going to lose all of your momentum, right? If you start with 500 and you come to a stop, that means your change in momentum was all of your momentum. So let's say that your change was negative 500. You have come to a stop. This is your initial momentum. If your final momentum is 0, that's a change of negative 500. So here's what we have. The impulse times the change in time equals negative 500. This is your change in momentum. So say that there was no airbag. There was nothing soft for the stuntman to jump into. He literally just jumped onto the ground and just splat. Yeah? That contact time is very small. Let's say that contact time is 0.1 second. Could be even less, yeah? If that contact time is 0.1 second, figure out how much force is going to be exerted on his body. It's going to be a lot. Okay, so I'm going to go ahead and actually erase these units so I don't get confused by them. So if the contact time is very small, again, boom, he hits the ground. It happens in that split second, he's come to a stop. We're going to divide by 0.1. And this is going to be the force that the stuntman's body feels. 500 divided by 0.1 is 5,000 newtons. That's a lot for a body to feel. It's going to hurt. Yes? Versus, let's say now he has an airbag. So what happens is he hits the airbag going with this much momentum. He is going to come to a stop. But what happens is the airbag absorbs him. And the time it takes him to come to a stop now is, let's say, 2 seconds. So force times change in time still equals the change in momentum. He still has lost all his momentum, right? He came to a stop. It's just that now he comes to a stop in 2 seconds. Go ahead and find the force. I'm going to keep that a negative, sorry. Go ahead and find the force now that his body would feel. Okay, so divide by 2. So the force he feels in this case is only 250 newtons. So that is a huge decrease of the force that they have to feel. It's going to hurt a lot less. So I hope this makes sense what impulse means. Again, to cause that change in momentum, we can either increase the time it takes for you to come to a stop, or we can have a very large force and very small time. Again, in terms of safety measures, it's better to have a long contact time and less force so it hurts less on you. So one more example to kind of wrap up with impulse here. Talk about jumping off a table, just to make sure we understand this. So just before you land, the floor is not moving, but you are. You're coming up to the floor, so you have momentum. After landing, both the floor and you're not moving. So you have lost all of your momentum. You jump off a table, and then you stop. You have lost your momentum. That means you experienced a change in momentum. So it says, how can you increase the time it takes for you to come to a stop, which would allow your body to feel less of force? Again, you are going to have a change in momentum, which is force times change in time. We just talked about We want to have a smaller force exerted on us and increase the time it takes to come to a stop in order for us to hurt less. Yeah? So what could you do as you land to increase the time it takes you to come to a stop? Just thinking this through. Well, this is why you bend your knees when you land. If you jump off anything, boom, and you land like this, locked knees, you feel a shock through your whole body, and it hurts. In fact, there have been cases where people have fallen off of houses or roofs, and if they land like this, they break their legs, they break their kneecaps, because they're experiencing such a massive force, because the time it took them to come to a stop is so great. So if you can bend your knees as you land, this increases the time it takes your body to come to a stop, which will decrease the force. Again, if I can increase time, I will decrease force, and vice versa. So that's what impulse means. To cause a change in momentum, this is what we have. Force times change in time. So to sum up one last thing, in the same way that work transfers energy into or out of a system, if you remember, work equals the change in energy. Impulse is the transfers momentum into or out of a system. So these are separate things. Once again, there is a difference, right? Momentum has a direction where energy does not. So remember, these are different things. Do not get them confused. We need to keep them straight. Momentum deals with velocities. Energy is speeds. So we're going to work with this in class, mostly with this concept right here, to hopefully get a better understanding of this.